Okay, we're going to be looking at a conservation of angular momentum problem for an isolated system. We're given here a block sitting on a frictionless table. It has mass M and is attached to a pivot by a massless rod of length L. A bullet hits the block in a direction perpendicular to the direction of the rod. It has mass small m and velocity v. And the question is, and we're going to focus on part A, what is the angular momentum of the bullet block system about a vertical axis through the pivot? Well, we're going to use the idea of conservation of momentum. Now, first thing we want to do is find out, or at least define the system. So what is the system? Well, we're going to define the system as the bullet, the block, the rod, the pivot, and the table. And all that's going to be our system, and we're going to shut it off from the rest of the environment. What do we know about the angular momentum of a system if it is isolated? You should be able to pretty much repeat this verbatim. If the system is isolated, then the angular momentum is conserved. Or another way to state that, the angular momentum remains constant. It is constant. What is the angular momentum before collision? We recall that the angular momentum is defined as r cross p, the cross product of the lever arm or the direction arm crossed with the momentum. Using unit vector notation, we can write that and we find out it's equal to minus mvl k hat. And we can see that because it produces a clockwise rotation looking down on the xy plane. The magnitude is given by mvl. What is it after collision? Well, what did we say? It's an isolated system, so the angular momentum remains what? Constant. So if it's constant and it's originally mvl, it's got to be the same afterwards. But we're going to have to write it in terms of the block bullet system now. And so mvl, but now the angular momentum of the block bullet embedded is given by minus I, the moment of inertia, omega k hat. And we can know what the moment of inertia of this particle, we're going to treat it as a particle, distance L from the pivot with mass m plus little m. So it's m plus little m quantity times L squared times the angular acceleration. And the magnitude is simply going to be m plus little m quantity times the lever arm L squared times the angular velocity. Now we're going to have to set that equal to the original angular momentum mvl, because our goal is to find this omega, the angular velocity. So can we find the angular velocity? Yes, because we know the angular momentum final must equal the angular momentum initial. Once again, it's isolated and the angular momentum is constant. So we now equate the original angular momentum, mvl, to the final angular momentum, m plus little m quantity, L squared omega. We consider that we know mvl and we know capital M and L. Our goal is to find this angular velocity omega. And we perform some algebraic steps and we find that the angular velocity is equal to mv over quantity m plus little m times L. Now we can go ahead and use that to solve part B, which I leave in your hands to determine.